Welcome to this week's Udacity Deep Reinforcement Learning Nanodegree Weekly webinar. So this week I'll be focusing from the multi-agent section and going over the research paper that was presented in the Udacity course. So what I've basically done is gone through the paper and broke it down into sections and just go over each bit one by one and sort of go into details a little bit of each and hopefully explain it a bit more. If you've already gone over yourself, hopefully this will clarify things a little bit more. Okay, so first what I'm going to do is I'm going to go through what we'll cover. So we're basically looking at the multi-agent anti-critic for mixed cooperative competitive environments paper. Go through basically introduction, related work, background, methods, experiments, and conclusion of future work. So hopefully, multi-agent environments are going to be getting used more and more. We've got a lot better at single-agent ones, and now we're sort of looking at how to get multiple agents to work together to, for example, Dota 5, StarCraft, done by OpenAI, sorry, by DeepMind, and OpenAI is Dota 5. So we're seeing it is starting to work and getting some great results. So we're going to go through some bits and pieces. So look, RL, reinforcement learning, we can, it's been applied to challenge games, robotics, all types of things. It's also getting used in industrial applications, large-scale systems, data calling, for example, at Google, where they were able to reduce their costs massively. Look, so far, RL has been really good with single-agent domains, and typically the other actors within it don't really make a difference, so we haven't really had to apply it. But there's a lot of things that are going to come out over the next few years that are going to involve multiple agents working together. Like I said before, OpenAI, that, but multiple things, cars, delivery stuff, robotics in factories, agricultural stuff, fishing systems, so many different stuff. Multi-agent self-play has also been used a lot. Great way of, so it plays itself to get better. So this is an interesting, with a lot of competitive software. And we're also getting quite good at, scaling our environments and having multiple agents learning. So, RL has moved a lot in the last few years, and it's only going to get better. But unfortunately, traditional reinforcement learning approaches such as Q-learning or policy gradients are poorly suited for multi-agent environments. One issue is that agents' policy is changing as training progresses, and the environment becomes non-stationary from the perspective of the individual agents. In a way, it's not explainable by changes in the agent's policy. So, the simplest approach to learning a multi-agent setting is to basically have independent agents. So you'd have individual agents learning, and this was attempted with Q-learning but didn't work very well. Independent learning policy gradient methods also performed pretty poorly. One of the main issues is that the agent's policy changes during training, resulting in non-stationary environments and preventing the naive application of experience replay. Previous work has attempted to address this by inputting other agents' policy parameters to the Q function, explicitly adding the iteration index to the replay buffer or using importance sampling. Deep Q learning approach has previously been investigated to train competitive problem agents. But let's look. So the native interaction between agents can either be cooperative, competitive, or both, and many algorithms are designed that one or only for a particular nature of interaction. Most studied a cooperative setting with strategies such as optimistic and heuristic Q function updates, with assumed that actions of other agents are made to improve collective reward. Other approaches is to indirectly arrive at a cooperation via sharing policy parameters. This becomes homogeneous agent. Anyway, these algorithms are generally not applicable to competitive or mixed settings. So, so the proposed similar ideas of using policy gradient methods with centralized critics tested approaches on different StarCraft micromanagement tasks. This approach differs from this paper in the following ways. They learn a single centralized critic for all agents, where we learn a centralized critic, centralized critic for all agents, where we learn centralized critic for each agent, allowing for each agent with different reward functions, including competitive scenarios. This method considers environments with explicit communication between agents. They combine recurrent policies and feed-forward critics, where our experiment uses feed-forward policies, although our method are through to recurrent policies. Here we learn continuous policies, whereas they learn discrete policies. Recent work has focused on learning grounded cooperative communication protocols between agents to solve various tasks. However, these methods are usually only applicable when the communication between agents is carried out over a dedicated differential communication channel. This method requires explicitly modelling decision-making process of other agents, and the importance of such modelling has been recognised by both reinforcement learning, cognitive science communities, stress the importance of being robust to decision-making process of other agents, as do others by building Bayesian models of decision-making. Here it incorporates such robustness considerations by requiring that the agents interact successfully with an assembly of any possible policies of other agents, improving training stability, robustness of the agents, and training. So, background of Markov games. So here we consider multi-agent extension of Markov decision protocol called observable Markov games. A Markov game, or n amount of agents, is defined by the set of states S describing the possible configuration of all agents, a set of actions, A in length, and a set of observations in certain length for each agent. To choose an action, each agent uses a stochastic policy, which produces the next state according to a state transition function. Each agent, I, obtains rewards as a function of the state and the agent's action, and receives a private observation correlated with the state. The initial state are determined by a distribution. Each agent aims to maximize its own total expected return, where y is a discount factor of t in the time horizon. Now let's look at the background of Q-learning and deep Q networks. Q-learning, a popular method for reinforcement learning, has been previously applied to multiple agents. Q-learning makes use of the action value function for policy. The function can be recursively written, and deep Q networks learn the action value function Q corresponding to the optimal policy by minimizing the loss, where Q is the target Q function, where parameters are periodically updated with the most recent, which helps stabilize learning. Another crucial component of stable and deep Q network is the use of experience replay buffer. Q learning can be directly applied to multi-agent settings by having each agent I learn an independently optimal function. However, because the agents are independently updating their policies as learning progresses, the environment appears non-stationary from the view of any one agent, violating Markov assumption required for convergence of Q learning. Another difficulty observed is that experience replay cannot be used. So let's look at policy grading algorithms. The policy grading algorithms are another popular choice for a variety of high-level tasks. The main idea is to directly adjust the parameter of the policy in order to maximize the objective. Using the Q function defined previously, the gradient of the policy can be written as, where the policy pi is the state distribution. The policy gradient theorem has given rise to several practical algorithms which often differ to how they estimate Q. For example, one can simply use a sample return, which leads to the reinforced algorithm. Alternatively, one could learn the approximation of true action value function, temporal difference learning. This is called a critic and leads to a variety of active critic methods or algorithms. Policy gradient methods are known to exhibit high variance gradient estimates. This is exacerbated in multi-agent settings since the agent awards usually depend on actions of many agents. To minimize notation, we will often omit delta from the subscript of the policy. Broad condition only the agent, only actions where the action of the agents are considered in the agent's optimization exhibit much more variety and therefore increasing the variance of the gradients. Proposition 1, consider n agents with the binary action. We assume an uninformed scenario in which agents are initialized. Then, if we estimate the gradient of the cost of the policy, we have the policy gradient estimated from a single sample and is a true gradient proof. The use of baselines such as value function baselines typically used for ameliorate higher variance. Background deterministic policy gradient algorithms. It is possible to extend the policy gradient framework to deterministic policies. In particular, under certain conditions, we can write the gradient of the objective. Since this theorem relies on the QSA, it requires that the action space and thus the policy be continuous. Deterministic policy gradient is a variant of DPG, where the policy and the critic are approximated in deep neural networks. DDPG is an off-policy algorithm and samples trajectories from a replay buffer of experiences that are stored throughout training, also making use of the target network as in DeepQ network. Methods for multi-agent actor critic. We have argued in the previous section that naive policy gradient methods perform poorly in simple multi-agent settings, and this is supported in the experiment. Their goal is to derive an algorithm that works well in such settings. They operated under the following constraints. The learned policy can only use local information, their own observation at the execution time. Do not assume differable models of environment dynamics. We do not assume any particular structure of communication methods between agents. And fulfilling the above would provide a general purpose multi-agent learning algorithm could be applied not just to cooperative games like explicit communication channels, but competitive games and games involving only physical interaction between agents. We accomplished our goal by adopting a framework of centralized training with decentralized execution. The policy to use extra information to ease training so long as this information is not used at test time. It is unnatural to do this with Q learning, and the Q function generally cannot contain different information at training and test time. Simple extensions of active critic policy gradient methods where the critic is augmented with extra information about the policy of the agents. More concretely, consider a game where n agents with policy parameterized by. Instead of all agents, then we can write the gradient of the 4 expected returns for the agent below. Here, Q policy is a centralized action value function that takes and inputs the actions of all agents, in addition to some state information, output the Q value. In its simplest case, X could consist of observations of all agents. However, we could also include additional state information if available. Since each Q policy is learned separately, agents can have arbitrary reward structures, including conflicting rewards in a competitive setting. We can extend the above idea to work with deterministic policies. If we now consider n continuous policy parameter, the gradient can be written as below. Here, the experience replay buffer contains the tuples, recording experience of all agents. The centralized action value function is updated. Centralized critic with deterministic policy works very well in practice and refers to as multi-agent deterministic policy gradient. A primary motivation behind MADDPG is that if we know the actions taken by all agents, the environment is stationary even as the policy changes since. This is not the case if we do not explicitly condition on the actions of the agents as done for most traditional RL methods. Note that we require the policy of other agents to apply an update. Knowing the observation and policies of other agents is not a particular restrictive assumption if our goal is to train agents to exhibit complex community behavior in simulation. This information is often available to all agents. However, we can relax this assumption if necessary by learning the policy of other agents from observations. Methods inferring policy of other agents. To remove the assumption of knowing other agents' policies as required, Each agent can additionally maintain approximation. This is approximate policies learned by maximising the log probability of agents' actions with the entry regularization. Here, H is the entry of the policy distribution, where the approximate policy Y can be replaced by the approximate value Y calculated as the following. Denoted the target network for the approximate policy. Note that can be optimized in a competitive online fashion before updating Q. The centralized Q function, we take the latest sample of each agent from a replay buffer to perform a single gradient step to update. We also input the action log probability of each agent directly into the queue rather than sampling. Now, method agents with policy assembly. So, a recurring problem in multi-agent reinforcement learning is the environment non-stationary due to agents changing policies. This is particularly true in competitive settings where agents can derive strong policies by overfitting to the behaviour of their competitors. Such policies are undesirable as they are brittle and may fail when the competitor alters the strategy. To obtain multi-agent policies that are more robust, policy of competing agents, we propose train the collection of K different sub-policies. As each episode, we randomly select a particular sub-policy from each agent to execute. Suppose a policy is an assembly of K sub-policies with sub-policy K denoted by. For agents I, we then maximise the assembly objective. Since different sub-policies will be executed in different episodes, we've maintained a replay buffer, I for each sub-policy, I of agent. Accordingly, we derive the gradient and assembly objective with respect below. Experiment environments. So to perform this experiment, we adopt a grounded communication environment that consists of N agents, landmark inhibits two-dimensional world and continuous space and discrete time. An agent may take physical actions in the environment and communication action gets broadcasted to other agents. Do not assume that all agents have identical actions and observation space or act accordingly with the same policy. We also consider games of both cooperative and all agents must maximize shared return and competitive agents have conflicting goals. Some environments require explicit communication between agents in order to achieve the best reward, while in other environments, agents can only perform physical actions. We provide details of each environment below. Environments, cooperative communication. This task consists of two cooperative agents, a speaker and listener, who are placed in the environment with 3 landmarks of different colours. At each episode, the listener must navigate to a landmark of a particular colour and obtain a reward based on its distance to the correct landmark. However, while the listener can observe the relative position and colour of the landmark, it does not know which landmark it must navigate to. Conversely, the speaker's observation consists of the correct landmark colour and it can produce a communication output at each time step, which is observed by the listener. Thus, the speaker must learn to output the landmark colour based on the motion of the listener. Although this problem is relatively simple, it poses a significant challenge to traditional RL algorithms. In environment cooperative navigation, in this environment, agent must cooperate through physical actions to reach a set of L landmarks. Agents observe the relative position of each agent and landmark and collectively rewarded based on the proximity of each agent to each landmark. In other words, the agent has to cover all of the landmarks. Further, the agent occupies significant physical space and are penalised when colliding with each other. Our agents learn to infer the landmark they must cover and move there while avoiding other agents. Environments keep away. This scenario consists of L landmarks including a target landmark and a cooperative agent who know the target landmark and are rewarded based on the distance to the target, M adversarial agents who must prevent the cooperative agents from reaching the target. Adversaries are accomplished by physically pushing the agent away from the landmark, temporarily occupying it. While the adversaries are also rewarded based on their distance to the target landmark, they do not know the correct target. This must be inferred from the movement of the agents. Environment physical deception. Here, N agents cooperate to reach a single target landmark from a total of N landmarks. They are rewarded based on a minimum distance of any agent to the target. Only one agent needs to reach the target landmark. However, a lone adversary also desires to reach the target landmark. The catch is that the adversary does not know which of the landmarks is the correct one. Thus, the cooperative agents who are penalised based on the adversary distance to the target learn to spread out and cover all landmarks so as to deceive the adversary. In this variant, environment predator-prey. In this environment, classical predator-prey game, N slower cooperative agents must chase the faster adversary around a randomly generated environment with L large landmarks impeding the way. Each time the cooperative agent collides with the adversary, agents are rewarded with the adversary is penalised. Agents observe the relative positions and velocities of the agent and the position of the landmarks. Environment covert communication. This is an adversarial communication environment where the speaker, agent Alex, must communicate a message to a listener, agent Bob, who must reconstruct the message at the other end. However, an adversary agent, Eve, is also observing the channel and wants to construct the message. Alice and Bob are penalised based on Eve's reconstruction, and thus Alice must encode her message using randomly generated key known only to Alice and Bob. Comparison to decentralised reinforcement learning methods. We implemented MADTPG and evaluate on the environment. Unless otherwise specified, our policies are parameterized by a 2-layer ReLU multi-layer perceptron with 64 units per layer. Support discrete communication measure we use and Gumbo softmax estimator. To evaluate the quality of policies learned in competitive setting, we pitch MADDP agents against DDPG agents and compare the results, success of the agents and adversaries in environments. We train our models and deal with convergence and then evaluate them by averaging various metrics for 1,000 further iterations. We provide the table and details, which I don't actually have on here. We first examine the cooperative communication. Despite the simplicity of the task, the speaker only needs to learn to output its observation. Traditionally, R methods such as DQ, network, act-critic, and first-order implementation, TRPO, and DTPG all fail to learn the correct behaviour, measured by whether the listener is within the short distance from the target. In practice, we observe that the listener learns to ignore the speaker and simply move to the middle of all landmarks. We plot the learning curve over 25,000 episodes for various approaches. Comparison to decentralized reinforcement methods. We hypothesized that a primary reason for the failure of traditional RM methods is a multi-agent method setting is lack of consistent gradient signal. For example, if the speaker utters the correct signal while the listener moves in the wrong direction, the speaker is penalized. This problem is exacerbated as the number of times steps grow. We observe that traditional policy gradient methods can learn when the objective of the listener is simply to reconstruct the observation of the speaker in a single time step, or if the initial position of the agent and landmark are fixed and evenly distributed. This indicates that many of the multi-agent methods previously proposed for scenario with short time horizon may not generalize to more complex tasks. So, comparison to decentralized. Conversely, MADDP agents can learn coordinated behavior more easily via a centralized critic. In the cooperative communication environment, MADDP is able to reliably learn the correct listener and speaker policies, and the listener is often 84% of the time able to navigate to the target. A similar situation arises for the physical deception task, where the cooperating agents are trained with MADDPG. They are able to successfully deceive the adversary by covering all the landmarks around 94% of the time when L equals 2. Furthermore, the adversary success is quite low, especially when the adversary is trained with DDPG, 16% when L2. This contrasts sharply with behavior learned by cooperative DDPG, who are unable to deceive the MAD. While the cooperative navigation and predator-prey tasks have less stark divide between success and failure, in both cases the MADDP agent outperforms the DDP agent. In cooperative navigation, MADDPG agents have a slightly smaller average distance to each landmark, but have almost half the average number of collisions per episode compared to DTPG due to the ease of coordination. Similar, MADDP predators are far more successful at chasing DDPG prey collision episodes, then collisions episode. In the cohort communication environment, we found that Bob trained with both MA, DDPG and DDPG outperforms Eve in terms of reconstructing Alice's message. However, Bob trained with MA, DDP achieves a larger relative success rate compared to DDP, so 52% versus 25%. Further, only Alice trained with MA, DDP can encode her message such that Eve achieves near random reconstruction accuracy. The learning curve, a sample plot shows that the oscillation due to competitive nature of the environment can often be overcome with common decentralized RL methods. We emphasize that we do not use any of the tricks required for cryptography environment, from including modifying E's loss function, alternating agent adversary training, and using a hybrid mix of transform, feed-forward, and convolutional architecture. We focus on the effective of policy assembly in competitive environment, including keep away, cooperative navigation, and predator prey. We choose K3 subpolicies for each keep away cooperative navigation environment and K2 for predator prey. To improve the convergence speed, we enforce cooperative agents should have the same policies at each episode and similar for the adversary. To evaluate the approach, we measure the performance of assembly policy and single policies in a role of both agent and adversary. We perform that agent with policy assembly are stronger than those with single policy. In particular, when pitting assembly agents against single policy adversaries, second to left bar cluster, the assembly agent outperforms the adversary by a large margin compared to when the roles are reversed, third to left bar cluster. We evaluate the effectiveness of learning the policy of other agents and cooperative communication environment following the same hyperparameters as previous experiment. We observe that despite not fitting the policy of other agents perfectly, the approximate listener policy learned by the speaker has fairly large KL divergence to the true policy. Learning with approximated policies is able to achieve the same success rate as using a true policy without significantly slow down in convergence. Conclusion and future work. We proposed a multi-agent policy grading algorithm where agents learn a centralized critic based on the observation and action of all agents. Empirically, all methods outperform traditional RL algorithms on a variety of cooperative and competitive multi-agent environments. We can further improve the performance of our method by training agents with an assembly of policies, an approach we believe to be generally applicable to any multi-agent algorithm. Another downside to the approach is that the input space of Q grows linear depending on what its information is contained next, with the number of agents n. This could be remedied in particular by, for example, having a modular Q function that only considers agents in certain neighborhoods of a given agent. We leave this investigation to future work. So now we're going to have a bit of a Q&A session. If you've got any questions, ask them now. Okay, no Q&As. Well, thank you very much for this week's webinar and wish you luck with all your work. Thank you.